Good morning. My name is Wenhao Sun, and I'm an assistant professor of material science and engineering at the University of Michigan. It's a great pleasure for me to kick off this morning's symposium, Data-Driven Discovery in Crystallography. Before I start, I'd like to thank the organizers, Dr. Olivier Gagne and Professor Anton Olinik, for inviting me here today. There's been a lot of excitement recently on using big data and machine learning to do knowledge discovery in material science and crystallography. But before we talk about that today, I'd like to start with a different knowledge discovery question. And that is, could a machine learn the structure of the solar system from planetary motion data? Now, there's two different structures of the solar system, right? There's the old idea of the geocentric universe, where the sun and the planets moved on shells around Earth. And the second is the heliocentric universe, where the planets move around the sun. Now, the heliocentric model is so obviously ingrained in our intuition that we think that maybe it's obvious that a computer would pick the heliocentric model. But actually, both models can predict the trajectory of planets pretty accurately. Now, what the geocentric universe has to do is it has to reconcile something called retrograde motion. Now, planets in the night sky do this thing where they track across the sky and come back and keep going. And the geocentric model actually deals with this quite well using something called epicycles, which were developed by Ptolemy. Now, remember, Ptolemy is a fantastic mathematician, so he's not a dumb guy. The way that he gets around explaining retrograde motion is instead of having planets on shells, he has planets on shells upon shells. And those are the ones that are going around Earth. And using this epicycle model, you can actually predict the trajectory of planets pretty accurately to about 900 years out, which is very impressive. And in fact, old mechanical projectors in planetariums use this model, which kind of makes sense, right? Because it's a geocentric representation of the solar system. Now, the reason why epicycles work so well is because epicycles are actually a Fourier transformation. And with a Fourier transformation, you can approximate any smooth function. Right? So here we can approximate the IUCr symbol if we have enough epicycles. The reason why I'm talking about this is because epicycles are a universal function approximator, and neural networks are also universal function approximators. Now, what I want to emphasize here is that if you have an epicycle description of the solar system, you might be able to get good predictions, but you don't want to get the right answer for what I would say is the wrong reason, right? You don't actually have planets going on shells upon shells. The reason why we are so innately drawn to the heliocentric model is because there's a physical mechanism of gravity in that model, right? And that's a very satisfying conceptual place to start our understanding of the structure of the solar system. And so, both the models give good predictions for the future, but maybe I don't really care about where Jupiter is going to be in 4 years and 3 days and 20 hours. What I really want is a conceptual understanding of the structural form of the solar system. And the reason why I bring this up is that if we think about chemistry, there's a very similar problem, right? Recently, there have been very exciting machine learning methods to try and make representations of chemistry. So here's a very impressive one, actually, where the authors read papers using text mining. And from the text mining, they built a TSNE representation of the elements, which clustered the elements actually very nicely together based on what we see today as the periodic groups. Here are the noble gases, here are some alkali elements. While this representation is very impressive, I would argue that it doesn't have kind of the conceptual value of the periodic table representation, right? Where, even in, elementary chemistry students are taught how to navigate this periodic table to, have atomic radius or electronegativity or where the metals are. Now, both representations are based on a big list of data, right? The elemental properties. Now, Mendeleev was a genius who took all these properties and sussed out some structural form, which is the periodic table. Now, what I want to ask today is, can we start moving machine learning away from representations like this into representations that give us conceptual insight, give us intuition about chemistry and material science? And I think my argument is that we can. We just have to have we have to satisfy two criteria. The first one is we need a good representation of the structural form. And I'll tell you a little bit more about what that means later in the talk. But the second one is that we also need features that may not be very convenient, may not be in any readily accessible database today. But if we can have a good representation of structural form and we have new materials features that are relevant to the physical situation, I believe that we can do very good knowledge and conceptual, intuitive knowledge discovery in big materials data. Now, everything I'm going to be talking about today is from a paper that I published 2 years ago titled A Map of the Inorganic Ternary Metal Nitrides. And so if you want to reference any of the content in this presentation in more detail, please go read that paper. There's a lot more discussion. Okay, so first, let me talk about nitrides, okay? So the reason why we were searching for nitrides is because nitrides are a very rare class of materials. Nitrides are solid-state inorganic materials that have nitrogen as an anion. Now, most metals in nature would rather oxidize than nitrodize, right? That means that even though nitrogen is 80% of the atmosphere, because N2 has a triple bond in it, it's not a very reactive anion, right? So while there are only 400 known unique nitride materials, there's over 4,000 ternary oxides. This is not even 400 known ternary nitrides. This is a mistake. It's actually just 400 nitrides total. So what's remarkable, though, is of the metals that form nitrides, if you mix and match the elements, you can actually form over 900 metal-metal nitrogen combinations. And so this compelled us to think that maybe there are new nitrides that had not been discovered yet, and we're going to use computational material science to discover those. Now, we use a pretty routine method in computational material science now for materials discovery. It's based on this idea of structure prediction. And the way that we do that is we first take all the known prototype structures in the ternary nitrides, and then we do rational chemical substitutions on them to extend the known ternary nitrides to a much broader composition space. Okay, and so what I mean by that is I might replace lithium with sodium, or iron with manganese, chemically meaningful substitutions, which we actually data mine, and it's discussed in this paper right here. We data mine which elements are likely to substitute for one another. And then from this, we take the few known ternary nitrides and we generate over 6,000 candidate ternary nitride structures. Now, these are all hypothetical materials. They may not necessarily exist, but what we do next is we evaluate the thermodynamic stability of these 6,000 compounds using something called the convex hull approach, which is very common in our field of computational material science. The way that it works is if you plot formation energy versus composition, then all the stable materials will fall in this lower energy convex envelope that connects the elemental reference states. So if I had a convex hull that looked like this, this line right here, and if I predicted one of these compounds in DFT to have a lower formation energy than the existing convex hull, that would be a new stable ternary nitride material. Or if it was slightly above the convex hull, it might be a metastable ternary nitride, which might also be synthesizable if we're clever about it. So in doing this technique, in taking the 6,000 compounds and calculating their thermodynamic stability, we make this figure. And this is a list of all the stable ternary nitrides today, and 213 of them were previously known. And in our work, we discovered 244 new ternary nitride materials. In other words, we have more than doubled the amount of known stable ternary nitrides. Okay. Now, I put this slide here kind of to impress you, but when we gave this to our experimental colleagues, they didn't even know where to start. It was like too overwhelming. It was like too much information. And so what we really wanted to do is kind of elucidate some more understanding and structural form from this. Can we understand where the chemical families are in this space? Kind of like how Mendeleev elucidated the structural form of the elements from his representation of the periodic table. So what we did was we started with data visualization, right? The first thing we did was we plotted on a heat map, which is this heat map right here. What we have are the axes are a variety of elements ordered by atomic number. And on this, each square is, if it's blue, it means there's a stable ternary nitride in that space. And the color of the blue, the shade of the blue, represents how stable it is, how deep the formation energy is. And when we look at this figure, we can already see some patterns appear, right? There are 4 lines that look very similar to one another. And what we can do is we can apply an algorithm called hierarchical clustering. And what hierarchical clustering does is it clusters together metals that have a similar propensity for forming a stable ternary nitride. And so when you do that, you can get this figure right here. Those 4 lines appear in this block right here. And some other blocks start to appear that were not immediately apparent in this previous representation. So this is a way that we can start to identify chemical families. And you can group on stable nitrides, but you can also group on other features. But okay, sorry, I skipped some information. Let me first talk about how hierarchical clustering works, okay? Because this is a data-centric symposium. So the first thing you do is you take each element and its reaction with all the other metals to form a ternary nitride, and you form a vector. So this is a 50 component vector, and we have 50 of these vectors, right? And so what we do is in this 50-dimensional space, we calculate the Euclidean distance between different elements, okay? And so when you do this, we find elements that are close to one another. So for example, these 4 lines are very close to one another in this 50-dimensional vector space. And in this hierarchical agglomeration algorithm, it'll group together elements that are close together until you form this tree diagram, or called a dendrogram. And this shows the distance between various elements and various clusters. And that's how you get to this figure right here. Now, you can cluster on stable nitrides, but you can also cluster on a lot of other features. You can cluster on the formation energy, or whether a compound is stable or unstable, or the periodic group. And a lot of this data comes in different forms, right? There's continuous representations. There's what's called nominal, which is a name-based representation, or ordinal, which is ordered. And you might want to cluster on a variety of things that are important to you as a scientist. It's kind of like when you go to Yelp and you want to look for a restaurant. There's might be a lot of criteria that you're searching for, right? Maybe you want something that's within walking distance, that's not too expensive, and is Chinese food or whatever. And so you might want to do a lot of searches based on specific features that are important to you as a scientist. And so the way that we do this here is that we combine formation energies, stability, metastability, instability, and chemical group into something called Gower's metric, which is really just giving different weights to different distances and creating a total distance out of that. And when you do this and you emphasize grouping stability together, you can get this stability map of the inorganic ternary metal nitrides. So this is a bigger figure. This is very overwhelming, actually, when you first look at it. But the more time you spend looking at it, you can start to see some trends appear. Okay, so blue, first of all, blue means that you have a stable ternary nitride there. If we look at this map, a lot of this region is blue, which is stable ternary nitrides. And then we see a predominantly green region, which corresponds to negative formation energy, but metastable. And then we see a region of red, which really is just unstable ternary nitrides. And each one of these squares is actually a full ternary phase diagram. So there's a lot of information in this figure. There's over 2,000 data points in this one figure alone. You can go to my website here and you can mouse over each square and it will give you the entire ternary phase diagram. And what we did when we had this figure is now we really started to see some trends appear in the ternary nitride space. Now we can start to see the chemical family start to appear. I want to emphasize one thing before we go any further, which is that there is no right way to order it. There's no ground truth ordering. You can order the information by atomic number or by, say Mendeleev numbers or using my agglomeration algorithm. There's, n factorial possible orderings. The best ordering is whatever you are looking for at that moment. In the same way that Yelp, maybe I'm looking for something that's important to me at that moment. And that's the way that I want to represent my data. And this is the particular way that we represent data to reveal chemical families. Okay. So here's the chemical families that we found. The first thing is that most of the stable ternary nitrides are comprised of alkali elements and a transition metal or a main group metal. This is a big block of stable ternary nitrides. There's also a big block of transition metal nitrides that are metastable. So these are materials that have a higher energy than the convex hull. And when we started seeing this, it took all that list data that we had earlier and it turned it into this visual representation where we started to see the families. And it just really made us ask, why? Why do the ternary nitrides have this particular stability relationship in that very extended chemical space? And to understand this question, to rationalize where the stability of materials come from, we tried a lot of things, and I'm going to tell you that story. And the bottom line is that we need good features to understand stability. Okay. The first thing that we tried to predict stability as a function of a variety of elemental and compound features, right? This is what a lot of people in our community do when it comes to machine learning. You make a big data sheet with elemental features and compound features, and you use some machine learning algorithm to make some functional form of stability as a function of all those elements. And this is something that we tried as well, and this is something that we got out. So like it would predict some reaction energy as a function of a very complicated functional representation of a variety of features that were really hard to understand and interpret. And so, here's a slide that I made a long time ago before the paper was submitted. And I was like, apparently the polarizability of the metal is important and the polarizability of nitrogen is important. And I said, I don't understand it. So what I found is that kind of like epicycles, right? In epicycles, if I were giving you an epicycle representation of the solar system, I think it would be very difficult to interpret that, right? You couldn't just look at the coefficients of each Fourier series and try to back out this idea of gravity, right? It would be very hard to understand. So I think in chemistry, it's also very difficult to project machine learned trends onto existing chemical intuition, right? Because the computer doesn't know any intuition. So it's just going to give you knowledge in the way that it represents it. Like if you gave a computer perfect information about a quantum mechanical system, could it back out the Schrödinger equation? I don't think so. So if you really want to give it, if you really want it to project out onto our existing chemical intuition, you have to give it features reminiscent of our intuition, right? So we used a technique called Lobster, which is a fairly well understood, or fairly well used computational tool now to build new features about chemical bonding in the solid state. The way this tool works is you have concepts of molecular orbital theory, and you extend it all the way to band diagrams. And so you can take the density of states of materials and decompose them into bonding and anti-bonding interactions. If you do this, you can start reprojecting back onto this triangle of metallicity, ionicity, and covalency. You can take one material, you can say where it is in this ternary space, and you can do this for all the ternary nitrides. And so when we do this for all the ternary nitrides, and we do this in a big data level, here's what we found. When you put the alkali metal nitrides onto this ionic, metallic, and covalent triangle, the Van Arkel triangle, a lot of the alkali metal nitrides that were stable were nitrogen-rich nitrides that were calculated to be highly ionic covalent. Remember, these are like semi-quantitative DFT schemes for bonding, for metallicity, ionicity, and covalency, right? And so we found that alkali metal nitrides were very ionic covalent, whereas transition metal nitrides were very nitrogen poor and very metallic. And can we rationalize why all these stable compounds are nitrogen rich with ionic covalent bonding? So what we did was we conceptualized this from the motifs that you see on a structure, right? So suppose you have some motif like A and B. Well, if A is an electropositive metal, A is going to donate an electron to its nearby nitrogen, and that nitrogen's electron density is going to grow. Now, what's that electron density going to do? It's not going to bond with the electropositive element. It's going to bond with the electronegative element, right? And in doing so, it's going to oxidize that transition metal. And if it oxidizes the transition metal very much, then it might even pull in additional nitrogen, which makes it nitrogen rich, right? And so if we look at the bonding motif of this final form, we see that we have very strong covalent bonding in the inside here, and you have very strong ionic bonding in the whole object. And this leads to ceramics with very negative lattice energies. And this explains why there are so many stable ternary nitrides that are alkali metal nitrides, right? You get materials like barium zirconium nitride, where you have a very electropositive barium, and then you have, that's a very ionic, and then you have these covalent zirconium nitrogen frameworks, and that this thing has a very negative energy, and that negative energy breaks that convex hull and gives you a stable ternary nitride. This is something that's known in the community as the inductive effect. Well, using the exact same DFT tools, we could also rationalize why there are certain islands of stability in the metal nitrides. Okay, in the metal nitrides, what we found was that most of them are metal rich or nitrogen poor, and they have a lot of metallic bonding. And what we found from analyzing the bonding was this: suppose that you have a particular chemistry where the metal bonds are stronger than the metal nitrogen bonds. Nitrogen, very surprisingly, can oxidize okay, even though it's an anion, it can actually oxidize a little bit. It can donate a little bit of its electron density to what? To reducing the metals. And in reducing the metals, it can form stronger metallic bonds. And that is actually another route to very low energy materials. Okay, and so we call this the reductive effect. It comes up with wonderful structures that I have never seen in any other kind of material before. Here's cobalt molybdenum nitride. You have a covalent molybdenum nitrogen network that is intertwined with this infinite metallic cobalt-cobalt chain. I just think that's a really, really cool structure. And here's another really, really cool structure. This strontium germanium nitride, which has an ionic strontium germanium nitride lattice, but this ionic lattice is interspersed with these infinite metallic germanium chains. I was like, what? Have you ever seen anything like that before? Like metallic chains in an ionic lattice? I don't know. I think it's remarkable. So this is the idea that we called the reductive effect. The nitrogen anion was oxidizing and donating electron density to the metal-metal bonds, and that is also a route to very stable ternary nitrides. So nitrogen has an electronegativity between oxygen and carbon, and we use this to rationalize the types of stable ternary nitrides that there are out there, right? There are oxide-like nitride ceramics, right, that are very stable. And there are also carbide-like intermetallic nitrides that are also very stable. And so this is a wonderful opportunity in nitrides to have a really wide span of materials properties for functional applications, which we think is very cool. So the title of my talk today was Unsupervised Knowledge Discovery in Big Materials Data. And what I argued was, if you want to have an understanding of the representation, you need to understand the structural form. Remember at the beginning, I was talking about the solar system, right? If we have a representation that is based on epicycles, you are not going to be able to get much conceptual understanding from that. But if you have a representation like the heliocentric universe, now we can learn something like gravity. So in this case here, I argue that, the proper representation was not a list of stable ternary nitrides, but by visualizing it and using hierarchical clustering, we were able to find the chemical families in this large extended chemical space. Okay, and that was what created this cluster map representation. The second thing that I argued is that if we want to understand the origins of stability, we weren't able to just use off-the-shelf machine learning methods with like this huge table of materials features, like elemental features and compound features. Like it gives us a representation that is a trend line, but from that, there wasn't very much conceptual, intuitive understanding, right? If you want conceptual understanding, you have to build new features that are based in your domain knowledge, in your chemical intuition, right? We built new features based on metallicity, ionicity, and covalency. And when we built those features, we were able to understand the stability origins of the ternary nitrides using these kinds of, new features that were really chemically motivated. Okay, and so that's the end of my presentation today. This is our talk on unsupervised knowledge discovery in big materials data. I just want to conclude with one more thought, which is that this idea of structural form is very important. Okay, it really grounds how we even conceptually approach a topic, right? If we think about the periodic table, a list is not very interesting. Even that TS&E representation was not terribly interesting. This representation, the periodic law, the law of periodicity, emerges from this representation, right? From the stability map, we had chemical families. Ashby plots, very important ways to represent trade-offs in material science, right? And also gives us opportunities to break the trends, right? The paradigm shifts in materials design. There's so many other representations. There's like the phylogenetic tree of life, right? And that helps biologists think about how evolution and structure of the animal kingdom comes about. We sometimes think about rankings when it comes to journal articles or schools or whatever. The way that you represent the structural form of your information is how you think about it. And so I think that if we want to better have a conceptual understanding and an intuitive understanding of material science and crystallography, we must first think deeply about what the structural form is. And when we do that, we'll be able to do unsupervised knowledge discovery. Okay, so thank you very much. That's my talk for today. And I think I have some time for questions left. All right, thanks.